Hey guys, how you doing? Corey back here again. It's been 2 weeks, I think, since I did this one. Didn't get time last weekend. Had it was midterm week, so I'm going to finish up a couple playlists that I've started for different subjects. So here's the vector class that we're working on, and this time we were going to finish it up by going over different error handling, because we said if you had the zero vector and you were calculating its magnitude, it gets a little weird. And I think last time I said the zero vector was perpendicular and parallel to every vector. It's just perpendicular. That was a mistake on my part. When we do cross products and stuff, we would get really long numbers, decimal numbers that we didn't really want. So I'm going to show you little cleanup things to just patch up all those little errors or just little inconveniences. So this one's going to be pretty quick. I changed one function somewhere in here. I think it was crossproduct last week because I was importing it to use in another library, and it was just convenient if I did one of the other formulas. I don't quite remember where it was, but if you notice it, it's still exactly the same. It's the same job. It's just one of the other formulas that you may have learned about when taking multivariable calculus or Calc 3 and stuff like that. So let's go through it. So the initialization is pretty much the same, I believe. They're just going to put in the coordinates, those tolerance values, so that if we get a cross product that's 0.00001, we're going to say, yeah, okay, they're going to be we're going to round it down to 0 and stuff. We're going to assume it's like that. DP is the decimal places. That's a new thing I put in, and that's just what the amount of decimal places we're going to round to. And by default, these are 0.01 and 3 decimal places, so not the most accurate, but I assume you don't always need something incredibly accurate. We just added in this little thing, value error here, and it's just going to turn on this error if you put in things that, if you put in A, B, C for the coordinates, it's just going to shout at you there. Or if you put in anything random, really that's not a number. Magnitude, no errors in there because it's okay if it returns 0 and such, but where it comes in is when we normalize it, because that's when we divide by the magnitude of a vector. And so we may, if we're finding the magnitude of the zero vector, we may get a zero division error. Okay? And for now, that'll break it. That'll say raise zero division error. But you'll see later that the next function that's calling normalize, if it gets that error, it knows how to handle it. So for now, it may look like, oh, we're going to raise a zero division error every time we try to do the magnitude of a zero vector. Well, that's not good, because then every time we have the zero vector, which happens, we're going to break it, which that doesn't look good, but you'll see in a little bit, it knows how to handle that. What raise does is it raises that error, and if somebody called that function, it'll throw it up to the next function. And if the next function knows how to handle it, it's all good. And we'll see that the next function knows how to handle it. Okay? Add vectors, subtracting vectors, there's really nothing you can get into there. Like subtracting and adding two numbers will never really give you something that screws you over, because the coordinates are made sure to be numbers up here. You're not dividing by 0, doing anything that will really break mathematics, so you're okay there. Same with scalar. Scalar multiplication, if you're just multiplying by a number. You could add in, when you call this, to check if that's a number itself, but you're going to get that error immediately thrown back anyway if you try to do this. So no need to do that there. Dot product, same thing. If you don't put in a vector, it'll immediately throw back an error on its own. And we don't really want to handle that in a special way. We don't want to say, oh, if there's an error here, do this special operation, because if it's not a vector, we just want to tell them, dude, there's nothing I can do here. It's not a vector. So that's still the same, I think. Here, the angle between two vectors. Okay, so that is when it gets interesting. Because what we're going to do is we have the dot product here. Okay, the angle between them. We do the formula where it's the dot product divided by the two magnitudes. But if we're calculating the angle between something and the zero vector, or if we're doing something with the angle of the zero vector, they're always perpendicular, no matter what, because that's the definition. If you have the dot product with something is 0, they're perpendicular. And if you dot product anything with the zero vector, it'll become 0 itself, which means that they're perpendicular. So if we get this zero division error, because if we call dot product, or over here if we, we don't need to worry about the dot product, but it's here when we divide by the magnitude. Because when we call the magnitude function, you see it's normalized, I'll throw there, but we may get 0 back, and when we divide by 0, that'll throw an error. So if we just get the error, just return 90 degrees. That's just math.pi divided by 2. I returned it in radians here. I'm defaulting to radians. We have this angle d if you want, because you see here, return math.degrees self.angle. So it just calls the angle function, returns it, and then just turns it in degrees using the math.degrees function. And you see this round that keeps coming up. Sorry, I forgot to mention that. The round function just takes in a mathematical operation and then the decimal places to round it to. So that's cutting off those really big decimal numbers we were getting by just putting in the decimal places that we specified when we made it. And don't worry, we may have added in a bunch of parameters and stuff. You may think, oh, the user or I have to remember that every time we want to pump this in. Well, I have, these default values that all you need to worry about is put it in the coordinates, and the rest are taken care of for you. Because these are all right values to use. If you really want to go different ones, you can put them in. So it's not going to really change how you use. If we put those in there, it's not going to change how you use it normally. It just gives you more options of freedom if you want them. So that's always something nice. If you can update your programs to make it so it doesn't change the user experience normally, but also gives them more freedom if they want to go explore that. So that's something I like to go for. So if they're perpendicular, we're going to try to dot product it, and we're going to try to check if it's within the tolerance. Basically all I'm doing here is doing really what we did up here with angle. I'm just calling the dot product, and if it's within my tolerance of 0, we're going to call it 0. And so I changed it a little bit last time. I had that big expression for if it's less than, I think I was over here, it was if the tolerance, or 0 minus tolerance is, greater than the value, or if 0 plus the tolerance was, this should be less than, or if 0 plus tolerance is greater than the value, return true, because that means it's within my tolerance range. But instead I can just cleave off one half of the range if I just do the absolute value and just call it less than. So if we got like a negative 0.0001, we're going to pump it up to just positive 0.00001 and check if it's within that tolerance. You can't always use this trick, but you can use it most of the time when you're using ranges, and it's really handy. I think somewhere in here I couldn't actually use the trick once. But it's really handy if you don't want to have those really long expression statements where people have to kind of like decipher what each case is and when it will happen. This is pretty easy to recognize. I'm just saying if the dot product is within my tolerance from 0, it's 0. I'm just going to call it 0. I'm not going to be very picky, and I'll just return that Boolean expression. Over here, we have accept 0 division error. That's just because, just in case any of these operations throw division by 0. I'm looking at it now, and I don't really see any cases in dot product. Right here, I'm not going to divide by 0 or anything. This is this is what changed. So I used to calculate the angle, and if there was, there's a 0 division error in angle right here. If that ever slipped through, I would just catch it and return true and whatnot, because if I'm dividing by 0, it means the magnitude of one of them was 0, and I automatically know that one of them is the 0 vector, and so I know they're perpendicular because the 0 vector is perpendicular to everything. That's a remnant of that. That doesn't really need to be there anymore because there's no errors. Just going to leave it there for now because I don't want to risk taking it out and throwing it in the air until I get time to test it. So parallel, here we can get I'm going to go down to cross product right here. So cross product, there's two formulas. There's this whole formula right here that we showed last time, and then it's the two of them. It's the cross product of two of them divided by the two magnitudes of them will get you the sine of, that's the sine of the angle between them. Mixing up my formulas here. But in cross product, I simply just unpack the coordinates of two guys, I pump it into the formula, and then I just round it using the decimal places. I just make a new vector with the coordinates. Remember, we're not changing any of the values of the vector functions. We're returning new vectors themselves. That way we can kind of, if you want, you can overwrite them because it's not like there's private variables in Python. But I am just not changing my vectors so that way I can preserve the old vectors. So I kind of get this chain of new vectors, but I can see where I got them through all the expressions for me. We just throw in one exception here. Value error is E. So if somebody threw in coordinates for like 4 or 5 dimensions, we're not going to do that here because this formula doesn't work for 4 or 5 dimensions. And I only use my vectors up to 2, 0, 1, 1, 2, 3 dimensions. And you see up in the initialization function, if they only put in like a vector and 2 coordinates, I add in a 0 for that third coordinate, just to throw that in there. The value error just makes sure that you don't put in any random extra coordinates in there that you shouldn't. In fact, you could even throw that in initialization itself, because then if you look, the dot product and such, actually this will work. Actually, yeah, dot product will work, because when you zip list, if I zip, I remember I was testing this, 1, 2, 3, if that's my first vector, and my second vector is 2, 3, 4, 5, like that, and I zip them, the resultant vector will, or the resultant coordinates will be, because in reality this guy's kind of like this, and when you do the dot product, this guy will get canceled out because he's being multiplied by 0, right? So the resultant zip, if I have them like this, should be actually, it'll be 1, 2, it'll really be tuples like that, but I'm just going to do these, 2, 3, and then it'll be 4, 3, and then it won't even do the last one, because they'll see this guy 5 has nobody to pair with, so it won't even do it. So it'll be as if 5 was multiplied by 0. So dot product will check out, scalar checks out because it goes through everybody. Add vect and subtract vect these guys only work if you do the bigger guy first, because if the zip thing will go away. No, actually these guys won't work either. Yeah, you probably want to throw that value error back in the initialization function, which I'll do after this video. So you can just basically throw this up into the initialization, or a form of this. You wouldn't throw this exact error, you would check the length, and you'd say, oh, if the length is greater than 3, throw maybe a value error, and say vector module only defined up to 3 dimensions, something like that. In fact, I'll probably just do that. Probably just show you if, and this is here is just in case they put in string values. In fact, this should be float. So if they put in like string of 3.1, if I did int, it would kind of ruin it or make it 3. So that should be float there. So if len core is greater than 3, raise, there's already a value here. Alright, I'll raise just a normal exception. Exception. Vector module only defined up to 3 dimensions. Okay. Let me look at this real fast. Yeah, that wouldn't work. Because then that final 5 wouldn't get done to the... Okay. If you really wanted, you could take this out of here, and you could have, what it does is it takes a copy of the one, if there are vectors that's smaller, just, like just up to 3 dimensions, the other guy's 4, you can make a copy of the first guy's coordinates and then extend them with zeros up to 4, whatever length that the other guy is. And then do the subtraction and return a vector with that set of 4 coordinates. That would work, but in this scenario, since it's going to come into odds with my cross product, I'm actually not going to do that. I don't even deal with vectors in 3D that much, or 4D at all, really. So I'm just going to leave it as 3D, but if you're ever in the case where you want to deal with vectors in 4 dimensions, you could make a copy of the shorter guy's coordinates and extend them with zeros. and then do this operation. And that way you won't lose any of the extra guys with the longer vector. But since it's going to run into exception, since it's going to get on odds with my cross product, I'm going to not do it. Exception as E. Just going to print error, and then I'm just going to add in E. And that will be my exception. Okay. Oh, it'll actually keep. Oh, yeah, this won't break out because it knows how to handle it, so it'll continue on with the vector. In fact, this should be raise exception. There we go. Alright. One more time of explanation of this one is when you raise an exception, it causes an exception, right? Same with, you may see this, assert. That's a Boolean expression. You know, if I x equals 2, and this returns false, it'll throw an error. So that's another way. I could say len, you know, I could even put it here. I could say assert len coordinates is equal to or less than 3, you know. And if that comes out to be false, it'll automatically raise an exception that'll break things for me. So that's a handy way to use assert if you don't want to do extra if statements and such. Because I used to see assert a lot in people's function. I had no idea what it meant, but I learned recently. Learned something new all the time. So parallel, I don't really need the zero division error as well, honestly. It's just, I really don't, honestly. But it's just a way for me that if there's a zero vector, it will like, somehow there's some errors coming up somehow with 0. Honestly, this is probably just a waste of space here. I think it's from my old formula that I had in there. I changed it for a little bit. I think it was, once again, calculating the angle and whatnot, and that's where you get division by 0. I just haven't taken it out now that I did the cross vector. You calculate the cross product, and if that's equal to just a vector of just zeros, you know they're parallel. Because the cross product of two parallel vectors is 0. So I think the old way I had doing it was it calculated the angle, and that's why I had the zero division error. Because if you're trying to test if it's parallel with the 0 vector, it's false. I really don't need it anymore. I'll probably take it out as soon as the video's over. But if you cross two parallel vectors, you get the 0 vector back. So if you do the vector like that, if you just make a vector without putting in coordinates, you see it defaults it to a blank list, and then it appends zeros to it if there's nothing, as long as it's less than 3. So if I just do a vector like here, like that, it'll just make a 0 vector. So I'm just saying if their cross product is equal to the 0 vector, return true, return true. Cross product is the same. Component 1, just return dot product. This zero division to error is just due to the normalization here, because normalizing I may divide by 0 due to the magnitude of a 0 vector is being 0. So if I get the error, I return 0, because the 0 vector has no component on anybody, right? So if this guy's returning a zero division error, I know I'm dealing with the 0 vector, and no matter who's projecting on who, it's 0. There's no projection or component of one guy on the 0 vector because it's length 0. Projection, same thing. I will just return the 0 vector in this case, because projection returns vectors, component returns a scalar component. So if I get the 0 division here when I'm normalizing, I know I'm dealing with the 0 vector again, and this time instead of returning 0, I'm going to return the whole 0 vector. So that's that. And then, yeah, that's pretty much it. That's the whole error exception thing. Just a nice couple handy things to make sure that you're dealing with your vectors right, and that nobody's putting any sneaky inputs in there. So, alright, so that's it for this playlist on kind of a vector linear algebra module you can use for many different things, like say you're making a game and you want to use vector forces to move it around the field. This is a way to do that. I've been working with some genetic algorithms recently, and seeing a lot of people use vector forces to make little shapes trying to win a game, you know. So this can be used even to do your homework if you really wanted to. Well, that's it for this. I hope you learned something new and had fun. See you next time.